everyone to the first talk of the Trinity term. So today we have with us Professor Launder from the University of Manchester. So I'll give a very quick introduction about Professor Launder. He received his first degree in mechanical engineering from Imperial College London, and then he continues his study to master's and doctoral levels at MIT, where he did experimental research on laminarization of turbulent boundary layers. The K-epsilon model introduced by Jones and Launder is considered to be the most popular K-epsilon model in turbulence modeling community. Following his election as a fellow of both the Royal Society and the Royal Academy of Engineering, he took on the role as the regional director of the Tyndall Centre for Climate Change Research. From 2009, he has edited and authored several books, official reports, and articles on climate engineering. Today, Professor Launder is going to talk about averting dangerous global heating through climate engineering. So let's welcome Professor Launder on stage.
Good evening, ladies and gentlemen. Real pleasure to be here. I was initially asked if I'd like to give a talk on turbulence modeling. Now, those of you who are in that field know that it's tons of equations and lots of abstract ideas. It seemed to me an absolute no-no to talk with you. But as you may also have picked up, some 15 years ago, I became associated with the Tyndall Centre for Climate Change Research at Manchester. It had recently started at the time, and I was feeling my way in. You heard I'm an engineer, I'm not a climate scientist. And I went to a conference which absolutely blew me away. It was a conference on geoengineering. Now, geoengineering is effectively what climate engineering has now become. Geoengineering has various other contexts, like, say, blocking off the Straits of Gibraltar so that the Mediterranean Sea becomes a lake rather than that sort of thing. That isn't what climate engineering is about. Anyway, so I hope today to present the essentials of climate engineering without personally professing absolute in detail every last nuance of the subject, but I think you'll go away, hopefully, with a much clearer idea of what is entailed. Well, to start at the very beginning, I'm sure everyone here is aware that the Earth is warming and getting too hot, and this is an old slide from the Meteorological Office, which does a pretty good job of showing why it's getting too hot. We've got the shortwave radiation from the sun that stops us becoming too cold, that is partly reflected by clouds. But then we have the long wavelength radiation emitted by the Earth, and that's a problem because the low frequency radiation is susceptible to getting trapped by greenhouse gases in the atmosphere, and that leads to, of course, to global warming. In fact, although we've only heard about that since the early 1990s, there was a century ago a Swedish individual here, Arrhenius. Anyone doing research in combustion will have heard of Arrhenius in a different context, but in this paper from 1896, he indicated that if you change the level of greenhouse gas in the atmosphere, you're going to have a big impact on temperature. A rise of 50% he asserts, if I can find the book, a rise of 50% would have the average effect of raising the climate by 3.5 degrees centigrade. We looked at doubling and increasing by 2.5 and arrived at these figures. Actually, his paper shows very detailed variations for different latitudes, but I've just clipped one entry there for a mid-range latitude. The effect of adding carbon dioxide to the atmosphere is, of course, very well known from what we know of our sister planets in our system. If we look at Mars, almost all the CO2 is in the ground on Mars. Its average temperature is minus 50 centigrade. Earth, average temperature around 15 centigrade. Or Venus, with a thick atmosphere, 96% CO2, average temperature around 400 degrees centigrade. Admittedly, they're not all the same distance from the Earth, from the Sun, but those differences are so stark that it should persuade anyone of the effect. Given that, and given that at least from the 1990s, we've been aware of the effect of CO2, what has been happening to the temperature, to the concentration level. Here we can see, starting at 1957 to 58, there's been an increase from about 315 in 2007-9 to around 380, 390 parts. Some of you may wonder what this red variation line is. It's almost a sinusoidal variation. And that arises simply from the fact that most of the vegetation on Earth is in the northern hemisphere. And so we've got our annual cycle here when the plants start growing, absorbing carbon, then we see that there's quite a dramatic fall, only to be reversed when autumn comes, the leaves fall, and we know the rest. You may say, well, that stopped before the crucial period when we should really be aware of what was happening. Just to assure you that things haven't changed, this shows the latest trends from 2015. 2015 is an important date because it's the date when the COP 2021 occurred in Paris, and everyone declared there, we'll see a bit later, that finally they'd solved the problem of global warming. We get perhaps an even more impressive link between temperature and CO2 level if we cast backwards in time. And I found this old slide really quite impressive. It shows both temperature, shown in blue and red when it comes up above this datum level. And what we see is that there's a very close connection between global temperatures rising and falling and carbon dioxide doing the same. Just to be clear, effectively here on the right-hand side is the present, and we may also note that there's been a huge increase very recent, within, on the sort of scale that I'm showing there in time, almost yesterday. Well, there have, of course, been querying observation. The data I've just shown may be a consequence of, as a result of rising temperature levels, CO2 levels going up. That is to say, CO2 dissolved in the sea. As the temperature rises, it releases some of the CO2. However, also there's the role of water vapor as well, which is also a greenhouse gas. Some assert that there's no real connection between CO2 and temperature change. And I've seen this data here presented to pointed out. This shows the variation of temperature between 2002 and 2008, and you couldn't possibly say that there's an upward link. Perhaps it's going the other way, as is often asserted, whereas the carbon dioxide concentration proceeds inexorably upwards. Well, you really need to look at a bit longer period. This is the same data shown over a 40-odd year time scale, and the data that are shown in the right-hand graph, these are on here, these are the results which are shown here. Okay? Some of the outcomes of rising temperature, I'll just flick through these. I think we're all well aware of them. We encounter severe storms, much higher winds. In the UK, we'll find surprisingly large waves, such as are shown here, but we only have to look in the region of the Bay of Mexico, and we find all too often hurricanes of increasing intensity as time goes on. Droughts and floods. Every undesirable climate consequence hits us. Now this next slide I found in a newspaper when I was making a flight on Air France. I remember being rather exasperated that they'd run out of English newspapers, and the only thing I could get was a Le Monde. And I just happened to look at this. This was shortly after I'd become aware of geoengineering, as it then was, climate engineering in today's terminology. And I was riveted by this crass assertion. It basically was in the business section of the paper. They were pointing out that hooray, hooray, to ship goods between Tokyo and Rotterdam would very soon become much more possible to do cheaply, because instead of having to follow these old routes, which are shown here, there would very soon be routes, northern routes, through what had been pack ice. This wasn't something that one could benefit from immediately, they asserted. They said a 30-year prediction of the benefits of de-icing the Arctic. Okay, this was a prediction from late 2004. I think it looks as though this desperate prediction is going to be fulfilled 10 years early. So who's to blame for all this? I would say governments, firstly, and international institutions, because they talk big about cutting CO2, but as I say on the slide here, they are way short of the target. And I mentioned the COP21 conference on climate change that took place in Paris in 2015. Here is the assembled dignitaries. You recognize Mitterrand, the President of France, on the right here, head of the COP21, the chairman of COP21, in the center. Grotesquely confident and rejoicing. But as we've seen when looking at what's happened to climate change in the year since then, there's been absolutely not a perturbation of effect. In the UK, we're often smugly complacent of what we've achieved. We've brought our CO2 emissions down, but we've also exported much of our heavy industry, all the industry that generates a lot of CO2, to the developing world. We haven't pursued renewable energy with enough energy and vigour, and I recognise that it's a sensitive issue, but we haven't adequately indicated the possibilities of limiting population growth. China, indeed, you'll know, adopted a one-child policy which they've been forced to abandon. So about 2 or 3 years ago, that was given up. But there are other things one can do besides being as brutal as saying every couple can only have a single child. One could encourage having children later in a couple's relationship. And then we come to personal lifestyle. A short break, 50 miles away, used to be the usual things. 2 or 3 days in the country or in the seaside. Not now, you fly somewhere, you enjoy a few days in Greece or wherever. You notice how many more SUV vehicles are around these days. You cast your mind back 10 or 15 years, they were very thin on the ground. Now they're everywhere. The ladies say, oh, they make you feel so safe to drive around with. And where does one have one's hen parties or one's premarital booze-ups? You don't go down to the pub. You fly to New York City, things of that time. And then after you've had your autumn short break in October and just enjoyed being able to sit out and take a drink on the terrace in Sicily or wherever, you come home and you think, oh, so miserable in England, how about installing a patio heater? Anyway, you get the overall impression, I'm sure. Some people say, don't worry, we're very strong in technology, we're very inventive, we'll find a solution, a technical solution that will make it all go away. We'll become carbon free. Even if that's true, and I sure hope it's true, it doesn't address adequately the question that the carbon dioxide we've now got in our atmosphere is really old carbon dioxide to a large extent. The rate at which it's being absorbed is very slow. So largely what because in a sense Britain, because it was the first industrial nation, those early releases made quite a contribution to the world total. So even if now you hear people say, we're only 1% of the CO2 release problem, we've got a very big history, however. And indeed, late starting is really what makes it likely that we must adopt climate changes later, and very soon indeed. So, to get to the topic of today's talk, I should first address what climate engineering is. And I've taken a definition from Wikipedia. It seemed quite a reasonable definition: deliberate modification of the Earth's environment on a large scale to suit human needs and promote habitability. And within this, there are essentially two very different approaches. and I'll say a little bit about each of the procedures. Firstly, carbon dioxide removal. Actually taking the CO2 that we've put in our atmosphere out. And there are various techniques that are approved. Of course, we've got forests, and as we've seen from the sinusoidal increase of CO2, forests are great, they help, but they're clearly not enough. But there are mechanical ways of taking CO2 directly out of the atmosphere, and that is what the proponents of carbon dioxide removal do. So here is a concept then of a plant for taking carbon dioxide out. We've got an array of fans here that induce air to flow through, and within the interior are means of identifying the carbon dioxide, removing it, and subsequently disposing of it. The other approach is what's known as solar radiation management, effectively reducing the amount of sunlight that gets through to the Earth's surface. I'll be saying then a few words about each of these. Firstly, direct air capture. These are the key players in this arrangement. Klaus Lackner was a professor when he first proposed the approach, was a professor at Columbia University in New York. David Keith is also an American, but was actually a professor at the University of Calgary, and has since recently moved back to Harvard. And then we've got another couple, also from Columbia University, Graciela Czerczyński and Peter Eisenberger. And finally, Aldo Steinfelder is from ETH Zurich, the one European on the list. And I've added two other names, and we'll come to those a little bit later. So, firstly, Klaus Lackner. As I implied, he effectively was the person that got the idea first, so he's often referred to as the father of direct air capture. 20 years ago, he actually published his first paper on the topic. And not only that, he proposed a scheme, successfully founded two companies. The founding was great, but they both went broke. Simply because there was not effectively the support, the underpinning support that inevitably is needed with a new technology like this. So he subsequently moved to Arizona and says that he's now simply in the business of doing research on strategies that are economically defendable for air capturing. And the picture shows one such device that he's currently showing. Basically, it's a dry-wet facility. One exposes carbon dioxide airstream to this apparatus that has a CO2 absorber in the panels. It's then immersed in water. That is to say, this rather Heath Robinson-looking contraption is lowered, and when wet, the CO2 is released and captured. So in principle, no heating is used in that arrangement. David Keith, I think, is probably the most believable of the other workers. Here's his installation, a test facility in northern Canada. Basically, his scheme involves a double loop, which I'll show here. Now, I'm not a chemical engineer. I gave up chemistry at the O-level, back in the days when there was GCV O-levels. But essentially what we see here is that aqueous potassium hydroxide interacts with incoming air with CO2 in it. The CO2 is absorbed in part to form potassium carbonate. That is then cycled through to a second reactor where effectively the reverse process is followed with calcium hydroxide, removing the carbonate attached with the potassium with calcium, and that in turn releases the carbon dioxide. Currently, they're sequestering something like 1 megaton of carbon dioxide per annum. 1 megaton is tiny, tiny. It isn't going to have any effect. But David Keith argues that when this is developed to a commercial level, they could remove CO2 for as little as $100 per ton, which is sort of the level at which the governments are talking of making the carbon premium, that is to say for releasing CO2. The Columbia group involving Eisenberger and Chochinitsky, here's a photo of them with the manager of their plant. They're rather vague about what it does. I won't really get out the piece I've just quoted there from their announcement. But here's a photograph. This is in Menlo Park, California, and it's attached to a conventional power station. The discharge from a local power station will have water at around 100 degrees centigrade, and that, what is called low-grade heat, is sufficient for them to operate. They claim, I'm not sure that they're correct, but they claim that they don't need any subsidy. They can extract carbon dioxide gas, pure carbon dioxide gas, in this way and sell it, and that will cover their costs. Finally, to Christoph Gebald and Jan Würzbacher, these, as I mentioned earlier, are students of Albert Steinfeld. They graduated, and on graduation they set up a company, working still closely with Steinfeld. And they've made quite remarkable progress. They have this company called Kleinworks. They've sold products in various parts, and well, as you see here, they've even exported one to Iceland, where in Iceland it's used basically to turn the captured carbon dioxide into a rock. What are you going to do with it? And one option, indeed the only option that was initially spoken about, was burying it. whether one buried it deep in the earth, put it at the bottom of the ocean. There were many proposals coming around in the early years of this century. But probably what is done occasionally is to pump it down oil or gas wells, and in that way you could extract more hydrocarbon fuel. As I comment here, that seems absolutely not the right thing to be doing if we're wanting to reduce our CO2 levels. Others have actually put into play a more productive use, to use it for CO2 in fizzy drinks. There is a market for carbon dioxide, and also industrial greenhouses. These people working with Aldo Steinfeld have done that. Basically, you need a sealed industrial style greenhouse, and here's one where they increase the CO2 levels to around 5%. 5% of the atmosphere. That's 100 times greater than it naturally occurs, in order to promote the growth rate of the plants they're producing. Well, that's great, but the scale on which we need to do this is so vast that one can't actually use us, if we were going to substantially bring down the level of CO2, you won't be able to do it in that way. What is much more attractive is basically to mix the CO2 with hydrogen in order to produce a hydrocarbon fuel. Now, of course, you have an energy input from doing that, but the net outcome is that you're not taking CO2 out of the ground. You're simply recycling already released CO2. And, well, as I note here finally, this is an area where, certainly in the UK, I know Sheffield and other universities in the UK are pursuing it. Also, several areas around the globe. David Keith, whom I mentioned, is very active in this area. However, having said that DAC looks as though is going to be developed, it's slow. It's going to take us 30 years, I'm sure, in order to bring CO2 down to a close, safe level. We know that governments react too slowly to foreseeable disasters. Basically, we need to have a disaster occurring tomorrow, effectively, for government to take urgent action. And in that event, if they finally say, we must do something fast, what we find is that the direct air capture is too slow. We've got to have a rapid response mechanism. And solar radiation management seems the only credible escape. So, how much do we have to do? The experts in this area say that all we need to do is to reduce the total amount of sunlight reaching the Earth by around 2%. Even if they're wrong, it might be 2.5 or 3%, say. It's still a relatively small amount. There have been a lot of proposals. Some of them can't be implemented in the short term. We've got the idea of space shields, or some very similar. Roger Angel has suggested lenses to steer incoming light away. And what this would amount to is putting up millions of these items. I've just shown one, but they would just be littering the regions 200 or 300 kilometers above the Earth. We've also got some balmy ideas. Moving the Earth from the Sun. But nevertheless, there are more down-to-earth, less exciting, but probably more workable schemes. And the most often spoken about approach is what's known as stratospheric aerosols. Essentially, one simply releases large quantities of a gaseous compound in the upper stratosphere. We know it works. It's one of the few things we have direct evidence of, because back in 1883, there was the Krakatoa earthquake, and that, we know, cooled northern hemisphere by over a degree centigrade. So, there's not that much more research needed in this area. There are issues, certainly fallout from putting these large quantities of gaseous sulfur compounds into the upper atmosphere. People are asking reasonably, what happens to the fallout? But if you quantify the outcome, it turns out to be much less than what we're doing already in our industrial plants around the globe. Okay, there are issues that aren't resolved. We've got its impact on local weather systems. They're not convincingly resolved, but they can be. So where one parts of the upper stratosphere where one seeds puts out these quantities of sulfur compounds, you would need to figure what the impact was going to be. There's another one. I want to talk a bit more about that. I'm not sure how much time I've got. I think there's enough time. And this is one that exploits the Toomey effect. What is the Toomey effect? It is that the greater the number of cloud condensation nuclei, that is to say, teeny particles on which water vapor can condense, the more of those you have for a given amount of water vapor, the brighter the cloud's reflectivity will be. You can just reflect more. So, if one raises the number of cloud condensation nuclei in this way, one can reflect the desired amount of incoming light. Here's a photograph taken from outer space, and you see these streaks here. These are ship tracks. They're not smoke. They're the fact that when a ship steams along from the funnels, lots of minute particles are contained therein, and these gradually migrate upwards. They're buoyant, and eventually they'll induce condensation, such as is shown here. Well, this point just explains what I just said. There are various ways we can think of introducing marine cloud brightening. That's I didn't perhaps use the term MCB before. No one wants to think that one's reducing cloud reflectivity, and thus making life on Earth worse. If you live in Manchester, as I do, you're especially sensitive to that. John Latham said, well, since we've got to put particles up there, maybe we should use the sea. The sea is salty. If we vaporize large quantities of water, the fine droplets contain salt. The water will evaporate, and one will then be left with a very tiny grain of salt at the head. And whilst 80 or 90% of the droplets that you produce are going to fall out, because the interactions are turbulent, some of them will be taken up and reach the layer at which clouds are formed. Now, John Latham had a colleague, Stephen Salter, and he said, well, the best thing to do in order to generate the least amount of extra CO2 by implementing this plan is to have unmanned radio-controlled vessels driven by Flettner rotors with Tom disks to improve the performance. Now, at this point, I'm going to slip in a little while a small amount of research that my group has done on this, but I thought it was worth introducing. As you see, both these gentlemen are over 80 now, and but they're still both very active. Here's Stephen Salter's suggested arrangement there. Here's his arrangement of a rotating discs, and we've got the water vapor coming out at the top. Let's look in a little more detail at this. If we go back a long time, many of you will have heard of the Magnus effect. Some of you won't. What we see here is that with a spinning cylinder is exposed to an airstream, there's a lift force on the cylinder. And in the 1920s, Anton Flettner, who was the sort of a 19th century equivalent of who was the Virgin Air travel? Richard Branson, thank you. Just escaped me. He had the idea that this might be a neat way to get rid of sails, and he was an entrepreneur, though, rather than a fluid mechanicist, but he was friends with Ludwig Prandtl. Those of you that are fluid mechanicists will certainly know of his name. And they had a very fruitful collaboration. So firstly, the Flettner bought this a sailing ship, converted it to 2 rotating cylinders, and it crossed the Atlantic to New York in record time, was given something like a ticker-tape reception in 1926. Prandtl, like most academics, was content by publishing a paper on the subject. And you might have expected things really to take off from there, but it didn't. We know that there was severe depression in the end of the 1920s, and the Flettner rotor was lost until the 21st century, when Innicon, the wind turbine manufacturer, decided that it would effectively, to show off, that it had clean credentials, had a ship built, Enercon 1, which you see here. The first delivery, the first working voyage of the ship was to deliver wind turbines to Dublin. It was rather symbolic, but still they claimed that they had a 30% fuel saving compared with regular propulsion. Anyway, back to these craft that Stephen Salter wants to produce. There are some technical details here, and the most challenging one, I don't go into any detail here, is the design of the spray generator. How you make sufficiently small sprays. That's a major area that research is being pursued both in Scotland and in the USA. How many ships would you need? Salter estimates that if we've got 2,000 of those worldwide, that will be sufficient to bring down CO2 levels. But I did mention Alexander Thom. You recall that the version that Stephen Salter proposed was this craft here with discs along it. Why was that? Well, this was due to Alexander Thom, and I thought I'd bring this in simply because Thom was a professor at Oxford University. I think he was the first professor of engineering after the Second World War. The research that led Thom to discover that discs were so advantageous wasn't done at Oxford, was done while he was a postdoc at Glasgow University, and this is actually taken from his paper. And what he found was that by attaching the discs, he obtained lift coefficients much, much higher than you had with a bare cylinder. And it was that discovery that led Salter's design of this flanged rotating column. However, I have to say that Thom didn't entirely appreciate what the rotating discs would have on the flow. So our admittedly very small contribution to this project in Manchester was first we were going to use computational fluid dynamics. We first would check whether we could predict how a bare cylinder behaved when you rotated it over a wide range of speeds, and then we would predict the effect of adding discs to it, and hopefully, this is what was envisaged, we then work out even better designs so that we could make them more effective. Well, we used traditional finite difference approaches, and here was the outcome of our research. Our points are showing then the variation. This quantity omega here is the ratio of the rotor speed to the wind speed. Okay, and what Thom had shown, as appeared in the earlier charts, were very, very high levels once you got the rotation speed above 4 times the wind speed. And, well, do we capture that? You can see in the various colored points at different Reynolds numbers, or effectively spin rates. What we can see here is that we broadly follow the trend at first, but no, we don't continue to rise, we level out. This was a mystery. We were thinking, what on earth can we do? Why aren't we mimicking this? And then we made an extremely valuable discovery, another experiment. Experiment by Brian Clayton. And his results mimic very closely our already generated, so there was no question about cooking the books, that his results align very well with our own data. The difference was he did his tests at a higher Reynolds number, and that, I won't go into the details of what that caused, but at any rate, it clearly showed that adding the discs was not a desirable outcome. So any future designs of these cylinders should be with a bare cylinder, not a rotating one, not one with fins. That is to say, unfortunately, although Alexander Thom made many contributions in fluid mechanics, although his data are accurate, they weren't representative of the conditions that would be faced. So that effectively brings me to the end, so let me just make some final remarks. I would urge you all to use every opportunity to persuade others that they should reduce their carbon emissions. Nevertheless, despite our best endeavours, I believe it's almost a certainty that we'll need to resort to direct air capture in order to keep the world safe. I think on the short-term basis, solar radiation management is also likely. I wish it wasn't necessary, but it seems to me that it will be necessary for a short period, and by a short period, I mean 20 to 50 years until sufficient air capture facilities can be installed to enable CO2 levels to be reduced. And of the various SRM strategies, I've said a little bit about the marine cloud brightening approach, which seems as though it has fewer adverse side effects than any of the others and is doable for a reasonable cost. I guess I should end by saying, as any research-based university person would say, more research is needed, isn't it? Usual. So my hope for the future, that you and your children will know better how to respond to this crisis, and that you will have a viable world to fix. I'm reminded of a colleague, John Shepherd is his name, also working in climate change issues. His wife happens to be a primary school teacher, and thus from John Shepherd to his wife gave certainly the class the information that John had provided, scaled down to be suitable for children of 7 and 8 to absorb, and they had a project, and they presented her with their answer for climate change, which you see here. And it's basically what they call a pedal bus rather than being picked up. Anyway, if the youngest generation can have that outlook, I'm sure we're going to be surviving. Thank you very much.
Thank you, Professor Launder, for the intriguing talk. Do we have any questions?
Thank you very much. So I suppose this is a sort of clarificatory question. The kind of upshot, as I saw it from this talk, was that it seems like we have quite comparatively viable alternatives to avoid some of the worst case scenarios that some of us might see as quite plausible in the current discussions of climate catastrophes. Do you think that's a fair summary to say that it's quite implausible that we'll see the worst case scenarios manifest for these kinds of potential solutions as viable alternatives? And in that case, why is it not more well known in contemporary discussions?
Of those working on direct air capture and SRM, there's certainly a hesitancy in making it too widely known, simply because one doesn't want the public to get to think, oh, no problem, we obviously will get another SUV rather than downsizing. So there is, I'd say, a responsible attitude there. Nevertheless, one wants to try and persuade governments, at any rate, to take action. When the Tyndall Centre was formed back in 1998 or 9, there was a big announcement that there were £6 million. But then you get to, and so all the universities, a lot of universities applied. Then you discover it was actually £6 million over 5 years, you know, so immediately it shrunk, and then funding was terminated because there was something more pressing on the government's agenda. They thought they'd solve climate change with that £10 million input. It's ridiculous.
Thank you. I was a bit surprised when you brushed aside the uncertainties of the impacts of SRM on regional climate, when most of the climate models that are being run at the moment indicate that the impacts of aerosols in the atmosphere on regional climate could be severe to the point of being politically impossible. So I wanted to ask, how do the climatic impacts of marine cloud brightening differ from stratospheric aerosols?
Well, let me get, so, can you hear me okay? Firstly, I didn't brush aside the problems with aerosols, but I didn't feel that it was more severe than, as I say, the industrial fallout. So far as what is the difference between aerosols and marine cloud brightening, all you've put up is water into the atmosphere. So it isn't the fact that you'll have fallout from dangerous clouds. You still have to face the issue of regionality, if you increase clouds in one area, get more brightening, what will you do to the climate? That all needs looking at very closely. And as we get better at predicting weather patterns, then one can actually directly address that. Does that at least partly deal with your...
Yeah.
You may disagree, but yeah, okay. Other questions?
Thank you for your talk. Does it work?
Just press the button underneath.
Yeah, just just press and hold it. Okay. Give it a couple of seconds. It should be okay.
Okay, good. Thank you for the talk. I have two questions. The first one is the solar radiation management. How much control do we have over it? I.e., can we reverse it if we wanted, or once the clouds are brightened, then they will stay this way?
Oh, you'll have to keep seeding them, yes. They will eventually, you'll have rainfall probably, and the clouds will disappear.
Okay. So this will need to
Yes,
be ongoing.
it needs, I mean, the vision that Salter has is that you've got 2,000 of these crewless ships continually steaming around the most productive areas. As I indicated on one of the slides, I may not have mentioned it, but the CFD calculations of climate indicate that the west coast of Africa and the west coast of North and South America are the most productive regions to see.
Okay, thank you. And my second question is, for the first strategy, the strategy where you capture carbon from the atmosphere.
Yes.
So you mentioned that the most attractive use of this carbon seems to be in recycling the carbon into fuel, basically. But I think in the long run, we probably want to have cars that run on electricity or something like this. So what's the long-term use of this strategy? Where do we bury it somewhere, but where?
Well, I'm looking, well, let's say over the rest of the 21st century. I am doubtful that we will get rid of CO2 release in that time. Maybe I'm a pessimist. I just can't see it. Certainly maybe in cars, but look at the industrializing countries. What they do is turn to coal. China has massive reserves of coal, and it's going to use them. It may be the most important producer in the world of solar panels, but it's the number of coal mines keeps on increasing. So I rather fear that that we're going to have CO2 being released all the time in the atmosphere. Once we get to a zero carbon world, we don't care. We can abandon either solar radiation management and direct air capture. But the companies that are forming don't think that's going to happen anytime soon. They're in it for more than 50 years.
Maybe comment on that. So there are certain things, I mean, yes, while you're right that electricity, we can run many things on electricity, but things like jet fuel is something which is extremely valuable, and it's very hard to believe we could electrify these systems. So that's where we probably want liquid fuels. And the other is, in the long run, you could probably also bury it in just the CO2 in disused gas fields without extracting more gas.
Yes, thanks for the comment about air fuels, because the concentration of energy contained in hydrocarbon fuel is so much higher than we can imagine by other means. I don't know, maybe an amazing new design of battery will be developed, but I wouldn't hold my breath.
Yeah, so you're in gas turbines a lot earlier on today. There's loads of people working all over the world on getting like 0.1% increase in efficiency on a jet engine. Are we wasting our time? Is there something better we could be doing?
That was a question I asked myself, since my main research was in cooling gas turbine blades in order to push up the temperature and marginally push up the efficiency of and you're not wasting your time. But don't look on it as it's fine for your PhD, but think of some other ways of deploying your skills thereafter.
Sounds good. Thanks very much.
Thank you very much. How are the costs and benefits of the various direct capture systems likely to compare with the costs and benefits of afforestation?
I'm unable to give you a direct answer, a definitive answer to that. It's not really my area, but $100 per tonne is generally looked upon as, and not only that, if one starts today on planting trees, it's going to take years and years before they're going to be really efficient in capturing the CO2. So I'm not saying we don't need to do that. We do. My guess is we need to do everything, and afforestation is certainly perhaps a scheme that can make a significant contribution with no ill effects. You can also look at the demands of afforestation versus growing food, population growing. There are conflicts there that I'm sure you appreciate. Thank you.
We have time for one last question.
Pick your favourite.
So I want to ask you, has it been modelled the effects on plant growth of what reducing the solar radiation by 2% would be, either for CO2 emissions or for food?
I don't know if that has been looked at. I would suspect the answer is no, that it hasn't been looked at, that one is looking at refining the modelling in order to be absolutely certain of what the impacts would be. But I mean, people have sort of mentioned that you're going to turn certain regions into an arid desert as a result of that, and that will obviously have impacts. I don't know of any papers that directly address quantitatively what the overall effect is.
Let's thank Professor Launder once again for the really intriguing talk. We're going to have a short networking session, and then we're going to head over for dinner. And we still have some spots left, so if anyone wants to join for dinner, please contact me or one of the